slides, right? That's okay. Pacing ourselves. This is slide 47, but I just want to go back a couple of slides to kind of get us right back in the groove of things where we left off talking last week. So, I'm just backtracking momentarily to slide 45, which is kind of our intro to what we're talking about today. So, arterioles. We move on from arteries, the big ones, and we move to the branches, smaller branches, leading into capillary beds, which would be arterioles. And at the arterioles, we already started talking about we can vasodilate at those locations, or we can vasoconstrict at those locations. And we have several mechanisms for doing such a thing, right? So we're going to divide, that's the bulk of our topic for today. So we're going to divide the mechanisms into intrinsic mechanisms. That's usually referring to kind of local stuff built into the arteriole itself. And extrinsic controls, which is something coming in from the outside and sort of influencing that arteriole in some way. And the extrinsic stuff we already know. Actually, we already know. We recognize sympathetic neurons, right? Releasing norepinephrine. And we had our reminder, which is the next slide of the table, right? Scary table. So we're going to take one reminder, look back at that. So we have that, and let's know that we have no parasympathetic influence on arterioles. Good? So, that situation, and then we'll have some hormones. We already know about epinephrine, right? We saw it in the sympathetic division, and we will see, I guess in the hormone chapter, we'll see this again, right? Epinephrine acting as a hormone, but being released in the bloodstream. We should actually know from anatomy, right? We reviewed that. Adrenal, right? Adrenal what? Okay, okay. Good. All right, so epinephrine, and here are two items that we have not talked about yet. We're going to talk about them an awful lot. Just a little bit in this chapter, but an awful lot when we get to the renal system and tie that renal system in with respiratory. Good. So you've got these two items. We'll know about them a little bit for now. We're going to know an awful lot by the time we get renal for these two items. Good. So they're on our radar now. Good. Let's see, that next slide was scary table, right? And what I bracketed off for this section of this chapter was this part here, where we've got arterioles as our organ, right? So arterioles, and then we've got maybe some specific locations where we'll find arterioles. I mean, those aren't all the locations of the whole entire body, but these are the biggies, right? So we've got arterioles, coronary, right? That's the coronary circulation, supplying the heart muscle itself. And then skin, skeletal muscle, abdominal viscera, that's all digestive stuff, kidneys themselves, and then salivary glands. Okay, they pull that out separately from digestive stuff because, well, they're not happening, right? So, they're kind of different. But we can look at each one of these locations, and remember, we've got arterioles entering in to the capillary beds that are going to supply those locations. And we can look under the sympathetic column and see in each location, do we use the alpha receptors or do we use the beta receptors, right? All right, so we take a look, and it also tells us in this column whether the result is vasoconstriction or vasodilation. Good? So far you see? It's kind of sensible. I mean, it's just you got to memorize it, but it's not. I don't think it's terribly difficult to understand, right? You just kind of look at it and for now, memorize. All right. So and then parasympathetic, we already said. I mean, there's our salivary glands, arterioles entering into salivary glands. Exception to the rule. We know by now that there are oftentimes exceptions to the rules, right? That's okay. But our rule was no parasympathetic innervation for arterioles. Good, and then there's our little exception. Good? All right, so we can, for this section, right, and this exam, which will happen a week from today, right, we can memorize that section. Good? All right, do not forget, just because we're focusing on this section, and we're going to add the veins to it a little bit, but just because we're focusing on this section, do not forget the stuff that you memorized for the heart, right, for today's exam. We're going to bring it back into the discussion today, right? But let's just, while we're here staring at it, and you guys just took the exam, let's be sure that we still have in the front of our heads, right? Beta receptors on these various locations on the heart, right? And then muscarinic receptors, right, in those locations on the heart. Good? All right. So, now we move on to, that was all extrinsic stuff, right? Sympathetic, okay, not parasympathetic, right, for arterioles, and hormonal stuff. We're going to acknowledge it, and we'll a little bit set that aside. We'll focus on that on renal, those hormones. All right, so the category above that was intrinsic control, using local events, right, or factors or something that are maybe intrinsic to those arterioles, right? They're kind of built in to the arterioles, good? As a way of getting the arteriole to vasodilate or vasoconstrict, good? So now that's what we're going to look at here. So, oops, I got a little bit cut off, but at the top here, that was, I'm pretty sure our first mechanism was active hyperemia. I think that was the first, let me just show you. Yeah. So see where we are? We're up here, intrinsic, and then active hyperemia. So this is the section that we're working on. Okay. So active, good. Hyperemia. Let's look at this word hyperemia. Emia is referring to blood, and then what do you think of hyper? What do you think of that prefix? Do you mean anything? Or huh? You think down, less? Who thinks more, and who thinks more for hyper, and who thinks less? Okay, so some think less. All right, so more, right? Hypo is going to be less. Yeah, so hyper, more. All right, so something about more blood, right? Maybe delivering more blood, right? To some organs, something like that, in some sort of active way, like on purpose, right? Okay, we can figure stuff out. All right, so let's look at this flow chart and see what happens. We always go to begin in our book, and what they're telling us is at the beginning of this process, the first thing that's going to happen, the first change that happens in the body is whatever organ we're talking about, we're going to go ahead and increase the activity of that organ, right? For whatever reason, there's going to be some reason before that, right? We're going to place an extra demand on that organ, and that organ is going to rev up its metabolism. Okay, fine. So that's where we're starting. So if we're going to increase the metabolism at whatever organ, the next thing that's going to happen is we're going to be, and we remember all of our metabolic processes, right? So assuming that we're going to perhaps go all the way through to oxidative phosphorylation, right, and have to use oxygen. The thing that we're going to do is use oxygen, right? And we're going to increase the production of our products, and we can refer to our products, right, as a group, as metabolites. So there's this word here, metabolites. And this is all going to happen if we're looking at an organ as a whole, not just one individual cell. So far, we've kind of been focusing on metabolism in like one cell, right? But if we take now the whole organ, we can look at the interstitial fluid that's in between the cells, right? And observe all of this stuff, concentrations of things changing also in between the cells as the cells use up things and produce things. So we're using up oxygen and we're increasing the production of these metabolites. And we have here a small list of examples of metabolites, especially the metabolites that are going to influence this process right here. So let's see. We know we're going to produce carbon dioxide. All right. We also know we're going to produce lactic acid. Where were we going to produce that, just to review? Like specifically which process?
Glycolysis.
Glycolysis, especially if we're in like an anaerobic, right, situation, we were going to, kind of take that little side trick. And lactic acid as an acid, right, we know from our discussion of acids and bases, right, we're going to release hydrogen ions. Good? Start getting used to thinking about acids and bases again. Because once we hit respiratory, right, which we start talking about the end of next week, we got to have that in the front, right? So, we got that. And then we have this item, nitric oxide, which we've mentioned a couple of times, right? Here and there, and I would say one little thing or one other little thing, and I kept saying, yeah, we're going to talk about it a lot more later. We're going to talk about it a lot more later, right? So here's later. Later's now. And now we're really going to start talking about nitric oxide in this section today and Thursday. So nitric oxide, gas, and it's produced and released by those endothelial cells. You remember last week we were talking about what were endothelial cells, right? We did that little anatomy review, and there was that table that had what are endothelial cells responsible for, right? Their jobs. So this is one of the jobs of endothelial cells, is to produce nitric oxide under these conditions, right? When we're undergoing some sort of increased metabolism, right, for some reason. All right, great. So the endothelial cells releasing nitric oxide, and this nitric oxide is going to act upon smooth muscle. Smooth muscle that's in those arterial walls, right? If we remember back to our anatomy and building an arterial wall, we have a layer in the middle of smooth muscle, right? So this nitric oxide is going to act upon this particular smooth muscle. Good? In the arterioles. All right, we're going to see more of that later. All right, but that's our list. You want to know the list. Good? All right. We've got this happening, and that is going to lead to that vasodilation in that arteriole, right? And right at that location. This is what we're talking about when we say intrinsic or local, right? Just at this location, we're going to vasodilate. So if we vasodilate an arteriole entering into the capillary bed of an organ, what do we do, right? So vasodilation was this. So what do we do as far as blood flow is concerned? Increase, right? Increase the blood flow into that capillary bed so that organ receives more blood. Good? All right, so that's kind of sensible. If the thing that triggered that in the first place was increased metabolic activity, maybe we started doing something, right, and placed extra demands on that organ, I mean, that makes sense. That kind of a built-in response, like automatic, right? Not having to rely on, sympathetic, all that stuff, right? Automatic response is, whoop, and then the blood flows kind of automatically, right? More to that organ. So it's pretty sensible, right? Just small, doggies. Oops, wait. There we go. So now we've got our next mechanism, right? Still within that intrinsic category, and we'll still use the word hyperemia, but we'll use, instead of active, we'll use the word reactive. Reactive hyperemia. So what do you think of that word, reactive? I don't know. What do you think of? Reactive. Yeah, response to something, right? I mean, technically that active thing, it was technically a response to an increased activity, right? But this is more of maybe something really, really physical. And I put it as the example at the bottom to explain it. If you were to put a tourniquet on someone's arm, right? Like let's say you want to draw someone's blood, right? They always put the tourniquet up here to kind of block the flow. And so, you're blocking the flow, and then when you release it, there's this momentary, sudden increase in flow, right? So it's more like that kind of a reaction to maybe something actually got cut off, right? Maybe the blood got cut off, and then when you release that and allow the blood access again, we're going to have for a few moments a whole lot more, and then it'll kind of equal out. Make sense? All right, so let's look at this next thing. Here we go. Flow auto-regulation. All right, we know about flow. What do you think of auto-regulation? What about auto? On its own, right? Like self kind of thing. All right, so auto, right? Not like car, right? Oh, did anybody drive by today? There was a car on Pico. It was a few blocks east of Sepulveda that had slammed into a fire hydrant. Did anybody see that? Oh man,
It's like,
flood.
like 5 blocks flooded.
Oh yeah. That's why I said several blocks. Oh my goodness.
Rough morning.
Huh?
That's a rough morning.
It was. I felt like there were a lot of angry drivers out there today. Like,
Imagine that driver though.
seriously, because that's, I mean, the angle of it and everything, I was like, what were you doing? Oh, man. So, anyway, that was a flood. That was a serious flood. I think that's kind of like this, actually, this flow thing. A lot of water. I mean, it's a little bit different, but let's see. Let's talk about this one. But that was pretty dramatic. It's amazing. What do we got? We're going to start over here with reducing flow, right? Or reducing pressure in an organ, and that will in turn reduce the flow. We've talked a little bit about pressure. We still have to have more fuller conversation about pressure a little bit today and a lot on Thursday. But after Thursday, you'll be able to tell me all the stuff that's in this arrow over there. So, decrease pressure, but we can imagine if you're not pushing fluid as hard, right, you're going to decrease the flow. That's the basics of it. We'll decrease the flow to an organ. So if we have less blood flowing into an organ, do you see how, let's look at the top two, we can get like the same thing happening that we saw in the first flow chart, right? For active hyperemia, we have not as much oxygen, but it's more in a sense of not as much oxygen arriving, right? Whereas before it was we were using up the oxygen that was already there. Good? So it's kind of the same in the box, but it's for a different reason. Good? And then we have increase in metabolites, different reason again. We've got less blood arriving, right? So we're not going to be going through metabolism as much, right? So we're going to have like a buildup of what was there because we don't produce it, but we also don't take it away. That's the other half of that idea. All right, and here's a new item. We decrease the stretch in the wall, right? If we don't have as much pressure, we're not pushing out on that wall, we're not having as much blood flow through, so, right, the wall itself becomes more relaxed. Think of it that way. All right, not stretched or relaxed. So, using this idea of flow auto-regulation or sort of controlling itself, telling itself what to do in response to this stuff, those arterioles will dilate, right? We've got everything kind of slow, kind of slow, kind of slow. If it dips just a little bit too slowly, right, to too slow or too low, you're going to kick in and the arterial walls will sense a little bit too low, right? You go a little bit, but not too low. So they're going to automatically, boom, dilate, and then we can increase that flow. Good? So we've got these mechanisms. They're so close, actually, right? They're so close, but it's these very subtle differences, and the subtle differences are usually the initial triggers. Good. And then we've got a lot of overlap here. Then things become sort of, the mechanisms become sort of the same, right? But it's the triggers that are going to be different. All right. So we've already talked about the extrinsic controls, right? Sympathetic. And let's see, we already know norepinephrine. We already saw a lot of alpha, right, receptors. And if we were to double check back on that chart, we would also notice that the alpha receptors seem to be paired up with vasoconstriction, right? So when we have norepinephrine binding to alpha receptors on arterioles, we're going to get vasoconstriction, right? So that's just in words saying what's on the table, right? That scary table that we already looked at. Okay, let's add a little piece of knowledge to all this stuff with the sympathetic and the receptors and all of that. We're always going to have, like let's say at rest, we're always going to have some sort of basal level of sympathetic stimulation happening. So we're never going to go to absolute zero as far as activity in those sympathetic neurons. We're always going to have a little bit, right? A little bit of norepinephrine kind of leaving all the time. Good? Just to keep us alive. All right. So it's from this basal level that we are going to either go up or down, right? And we will not go down to zero, otherwise, you could pedal a flight. All right, so, I guess I put that in. Wow, did I put the whole rest of the slide in bold? My goodness. And there's like italics there. Wow, that must be important. Like the second half of the slide. Let's see. So, here's arterioles. Let's review. Remember I told you, I warned you, right? Don't forget your cardiac stuff. Like it was just today's test, so don't forget. In cardiac muscle, we had mostly the beta, right? Receptors, for that norepinephrine. So that's separate. We're releasing, think about it, right? Think about a sympathetic situation, right? You were panicked about the exam, right? Out there, everybody panicked about the exam. And lots of norepinephrine being released at that time. And both alpha and beta receptors are capable of binding all of that norepinephrine, right? So, I mean, norepinephrine's not going to care, right, whether it's an alpha receptor or beta receptor. It's just going to fit, I'm going to go there, right? So, if it's binding to both, that norepinephrine that's all circulating now, because our countdown begins, exam coming up, oh no, right? So all that norepinephrine that's circulating is just going to bind wherever it fits, right? Whether it's alpha or beta, norepinephrine doesn't care. So, do you see why it's important to know the different locations, right? Because if we're binding at, let's start with the heart, because you guys already know that. If we're binding at the beta receptors, right, on the heart, all the locations of the heart, what happens again at the heart? Right, we increase contractility, and what? I was just saying everything. It increases everything. So we've got contractility, we've got heart rate. Okay, conduction, right? That's going to factor in, exactly. Okay, good. That's going to tie the two together, right? All right, so far so good. Right? So we're increasing heart rate, we're increasing, what maybe is the result of that? Cardiac output, yeah, that is it, right? Ultimately, we're increasing heart rate and stroke volume with that contractility, right? Increased cardiac output. So we're pumping more blood out, right? That's what cardiac output is, right? So we're increasing cardiac output, we're pumping more blood all around. Good, so far? All right, if we're pumping more blood all around, should we do something with the vessels? Probably. I mean, that's going to be the topic of the whole week, right? Is how do we do that and why? But to start off this conversation, it probably, right, would be smart. We're going to start pumping more blood all around, the blood vessels should respond, right? And we've already said that most of those arterioles, right, arterioles had which receptors again? All right. Except, let's see, I think, is it on here? Is it on here? Let me just review before we leave the heart. I know I pointed it out. One thing to note. Coronary arterioles, right? The actual arterioles that supply the heart muscle itself. Take a look. Yes, alpha, right? But beta in a big way, right? Beta in a big way. So, and let's also look at this pattern that we see. Alpha, let's see it for sure on the chart. Alpha, vasoconstriction, right? Beta, vasodilation, right? Okay, now let's go back to what we were talking about. If we start with coronary blood vessels, right? Coronary blood vessels. If we are increasing all this work that the heart has to do, right? Yeah, what would be smart? Yes. It would be smart to dilate those very arterioles that are supplying the heart, right? So those beta receptors are the ones that are going to be more influential at that point. Make sense? Under this sympathetic stimulation. So far, so good. So now we've got the heart itself taken care of, right? As far as what it's doing, we already know this stuff, and how are we going to supply that heart muscle with additional oxygen and glucose? Good. We'll increase its blood supply by getting that norepinephrine to bind to all those beta receptors also on the coronary blood supply and get those blood vessels to vasodilate. Good? All right, so far so good. And now we're going to pump all this blood out to everywhere else. Everywhere else. And we have already said that a lot of those arterioles have alpha receptors, right? Alpha receptors. What was our thing about alpha receptors and blood vessels? Arterioles specifically? Constriction. So it seems like a lot of those arterioles, if they've got so many alpha receptors and really not very many beta receptors, which is the situation, right? For most of our arterioles, we're going to have one huge exception. Huge. But if it's mostly alpha receptors on most of our arterioles, we're getting vasoconstriction in most of the locations. Let's think of some locations. I mean, we can always look back at the table, which we probably should. But let's say digestive stuff, right? Let's start easy. Simple. Digestive organs. Arterioles into digestive organs, if they're all covered with alpha receptors, right, which they are, and the norepinephrine, all right, I'm going to bind to these, right, and we're going to vasoconstrict those. Does that work for us? Does it work? Yeah? Entering, like the ones leading into capillary beds for digestive stuff? Because in a sympathetic situation, we're wanting to turn down digestion, right? So that totally makes sense. It also explains why when you're nervous or worked up or scared about something, sometimes the eating doesn't work out so well, does it? And then you get the stomach ache. Should have eaten that right before taking that exam, right? Nerves, right? Okay, that explains it. All right, so far so good. But this huge but. What about like skeletal muscle? Because we've talked about already, right? We even talked about it in anatomy. The whole thing, I mean, part of the whole thing about sympathetic division and fight or flight was Oh, you were either gonna run away or you were gonna kick somebody in the head. Roundhouse kick, right? Yeah. You know what? In the summer, when I talked about roundhouse kick to the head, there was actually a woman who, her daughter, raise her hand, her daughter, who's like 8, is like some karate like champion in the state, and she goes all around and competes. And she showed me actual footage of her daughter doing the roundhouse kick. It wasn't to someone's head, but it was pretty dang good, right? To see a little girl. Woo! So, seriously, one of these days, I'm going to learn from this girl. Do it. So that demo. I gotta learn. Alright, so anyway, what was the deal? What was the deal if you wanted to roundhouse kick to the head or run away? Either one, doesn't matter. What did we have to supply with blood, right? What muscles? Skeletal, right? What should we do? What should we do? What should we do before we look at it? Maybe we could think it out, right? What should we do with the arterioles entering into the capillary beds to skeletal muscle?
Dilate.
It would be better to dilate them, right? So, should we pick a different setup?
Yeah.
Of course. We should. That would be smart, right? Okay. So that's what we're going to do. We're going to see that. I think it comes up like in the next slide or something like that. Let's look. Oh, yeah, it is. Okay, good. Okay, this slide. I know this looks terrible because not only are there kind of a lot of boxes and an arrow going in a weird direction, but there are a lot of additional words around it. But this slide, please know this slide. Please know this slide. For, of course, next week's exam, but also for the final, right? Because this is one of these concepts, right? One of these complex concepts that if you can grasp this one, right, you can kind of explain everything around it, right? And that will get you very far for the final, right? If you can explain a whole bunch of stuff that leads into this slide or is around this slide, right, but not on this slide. All right, so let's take a look at the situation in skeletal muscle. Not on the skeletal muscle cells, but on the our smooth muscle. See, this is tricky. It's on the smooth muscle of the arterial walls that lead into the capillary beds of the skeletal muscle. Do you see it? That was a really long sentence. It's really long. So, okay, skeletal muscles supplied by blood vessels, capillary beds, the arterioles leading in have smooth muscle in the walls, just like all of them, right? It's those smooth muscles, right, that have many beta receptors, not so many alpha receptors, right? So if we really, really pack that location, right, with a lot of beta receptors, we can go ahead and vasodilate. When we release a whole bunch of norepinephrine, right? And also epinephrine from the bloodstream, right? We can get both, as always, we can get both. And we see that here, norepinephrine coming from sympathetic neurons, and we see epinephrine floating around in the blood, right? And originally that came from the adrenal medulla. Make sense? So they're going to bind, good, and we get our vasodilation in the arterioles, right, the smooth muscle of the arterial walls feeding our skeletal muscles. Make sense? You've got to get that whole sentence in there.
So the arterioles are made of smooth muscle, but they're in the capillary beds of skeletal muscle.
Right. Exactly. That's the thing that you want to be really clear on, because you know how I'm going to write that sentence. Right? Or maybe the choices. Like maybe I'll do a good job on the sentence, and then like the choices are going to be right, murky. Okay, so Be sure. We already talked about why, right? We already talked about why you would want to vasodilate, right? Leading into those skeletal muscles. Because we're going to run. We're going to do the run. All right. Very good. Be sure. Be sure. All right. So, here is a summary of all of the controls, intrinsic and extrinsic, plus this particular chart shows some extra stuff. I put the extra things that we have not discussed in parentheses. So stuff in parentheses, don't worry about for our exam, right, or for our final. But I left them in there because I always feel bad, like just like blotting something out, like deleting something or something like that. I feel terrible. So I put them in parentheses because we know they're there, but we're not going to worry about them for the exam. All right. So everything, all these controls are leading to, this is the super important thing, smooth muscle in those arterial walls, right? And these arterioles, in turn, would be, like we could put more hours if we really wanted to, would be leading to this organ and that organ and this organ and that organ, right? All right. So just so you know, we've got 3 categories up there. The local controls are those intrinsic ones, right? We recognize these especially over here. And let's see. And this was sympathetic, and then hormones over here as extrinsic, right? So these 2 are extrinsic controls. Good? And here, just so you know, I know I put this in parentheses, even though we talked about nitric oxide, over here, it turns out that there are neurons that will release nitric oxide, but we focused our discussion on endothelial cells that release nitric oxide. Good, so this is the nitric oxide that I want you guys to know, right? This is going to come back and haunt us when we talk next week about clotting, blood clotting. So I want you to know this. And let's keep in parentheses that nitric oxide that's released by neurons, because that's kind of a small item. Good? So focus on this nitric oxide that's not in parentheses that we talked about. Intrinsic. Good? Endothelial. Good. Woo. All right. Oh my. Okay, so this table, I guess, just a reference. There's an awful lot of words in there. But a lot of this stuff we kind of talked about in general, right? And this is just, looking at individual organs, like looking at kidneys, looking at brain. But we really focused on like digestive organs and skeletal muscle and heart. So we kind of focused on the top 3 and talked a lot about those. And here, they're just giving us more of similar information, right, for a few other organs. Specifically, they picked out kidneys, brain, skin, and lungs, right? So this table, kind of like I wrote in the upper corner, this is more for reference. You can read through them, and hopefully that will help you to understand all this stuff that we talked about using, again, digestive, skeletal muscle, and heart as our examples. Good? All right. Let's see. So, all right. So we're going to move on to capillaries. We're talking about arterioles leading into capillary beds, and how are we going to control those? So ultimately, we want to enter into the capillary beds because that's where we're going to exchange oxygen, carbon dioxide, glucose, right? Stuff. So this is anatomy review for structure of a capillary. And anatomy review, structure of capillary bed. And here would be our arteriole, right, entering into the capillary bed, and then our venule leaving the capillary bed. All right. General stuff about capillaries. Depending on what we're kind of doing, we might have 5% of the whole blood circulation hanging out in those capillaries. That can certainly change. We'll find capillaries everywhere except in the cornea, which is perfectly clear so that we can let in as much light as possible. And that's a lot of mileage, right, for an adult body. Capillaries, that's incredible. Right? Wow. So, let's talk a little bit about flow into these capillary beds. So if we assume that this part of the drawing here is representing an arteriole entering into a capillary bed, and here's our capillary bed with, looks like 6 individual capillaries, right? It doesn't matter, it's, you know, just made it into 6. So we've got these individual capillaries, and that's representing the capillary bed. And these balls are representing the blood flow. So they're telling us, okay, we can have in the arteriole this much blood move this distance in this time period. They gave us a minute, it's fine. And once we sort of send all that blood to the different branches in the capillaries, it slows way down, and we're only going to move this far in that same amount of time they gave us a minute. All right, so we can kind of plot that idea on a graph, of course. Physiology is all about graphs, apparently. What do we got here? In the upper part of the graph, we've got area, right? And in the bottom part of the graph, we've got velocity, so the speed, right, of this flow. And we see here they're dividing the graph over time, also into areas. So we've got the aorta, we've got arterioles, and then we've got capillaries, and then we're going to collect everything in venules and veins. So we see here, we increase the cross section, right, because we have so many branches of capillaries. So this line goes up, but as that goes up, the flow slows way down, right? So that's this green line. The velocity, we're slowing down the flow. All right, so that's kind of good, right? Because once we're in the capillaries, we're trying to exchange oxygen, carbon dioxide, glucose, that stuff. It would make sense to slow everything down so that we can do that, right? More efficiently. If you just fly through there, right? Can't really exchange. Okay, so that totally makes sense. And now we have to talk about the exchange, right? So here are the items that we are going to exchange. These items should look familiar, right? From metabolism, right? Our biggies, glucose, you know, oxygen. We know, we're going to know oxygen so well after respiratory system. It's going to be nuts. Carbon dioxide, we also know, we're going to know it even better also after respiratory system. Yeah, we have water and ATP. All right, we know those. But one of these is kind of really biggies, right, that we have to sort of deliver and pick up. So we have to somehow get these items from the capillary. Here they're giving us an example of muscle. We recognize this as a muscle cell, right? So somehow we have to get these items from inside the capillary through the interstitial fluid, right, and into this muscle cell. All right, and assuming that this muscle cell is working, right, as always, we also have to get the carbon dioxide produced through the interstitial fluid and then back into the capillaries. All right, mostly we're going to use diffusion for these items to sort of pass through these I don't want to say pathways, but these locations. Good, so mostly diffusion. Here's just a reminder of stuff that can easily diffuse, anything lipid soluble. Good. Oxygen, carbon dioxide, lipid soluble. Things that are either ions or polar, as long as they can kind of squeeze their way through, maybe in between cells, fine. It's fine. And here's just something that we should know. This will come back. This will come back to haunt us in a while. But in some locations, we were going to have big intercellular clefts, right, when we build that capillary. So this will come back from anatomy to haunt us. All right, let's see. Building up to the uh-oh slide. It's not yet. Reminder from day 1. Remember day 1 we learned about extracellular fluid? And we could divide that, right, into two compartments. And remember, I wanted you guys to learn the volumes. Okay, I told you, right? I warned you. There was a reason why I wanted you to learn those volumes, because we're going to see them again. And today, yeah, we're like halfway through, right? We see them again. Woo! I warned you. All right. So plasma, obviously, in the capillary. Interstitial fluid, we know where that is, right? In between the cells, but outside of the capillary. So we saw from that previous slide, we'll have stuff moving, right, from capillary to interstitial fluid, and we'll have stuff moving from interstitial fluid into the capillary, right? Let's add vocabulary words. Filtration from the capillary to the interstitial fluid. Absorption, reverse, right? Interstitial fluid into the capillary. Become friends, right, with these words. These words are all over the place from here on out till the final. Good? All right. Oh, this is the slide. Yeah. The two slides of the day are the one that we looked at on skeletal muscle, right? The arterioles leading into skeletal muscle, that one, and this one. This is the other slide of the day. How are you guys feeling? Let me see. We're in good shape. You want to do this one? No. Before break, or you want to take a break and shake your heads out? This one kind of has math in it and stuff. This is a big one. All right, so let's do a break. We'll come back at 10 after 9.